Thank you, Tim. And thanks, of course, big thank you to Michał and Piotr for inviting me to this workshop. I also would like to apologize. I think it never happened before that I didn't send in my title and abstract, but the messages of Michał and also Krzysiek reached me when I was, I think, at 4,000 meters. So it's the only luxury I allow myself 3 weeks a year to completely switch off. So sorry about that. I will talk about quantum effects in cold collisions because that's what interests me. What is quantum as we go cold, and what quantum effects can we see with molecules? And here's an overview and a picture I stole or adapted from one of Bas's papers that I like a lot because it highlights this point. So the first point is we see the wave nature of matter, for example, in diffraction and interference patterns when particles collide at very, very low energy. But this is not the only part that becomes relevant as the wave nature of matter emerges. You can also ask yourself about questions, does the internal quantum structure of the scatterers play a role? Like here we illustrated point particles. It's not that simple. We have tunneling, we have quantum reflection, and maybe more effects. So you probably have seen this picture before. Going cold means freezing out partial waves. And one of the hallmarks of being cold is that then quantum scattering resonances become really pronounced and dominate the collision dynamics. And one of those resonances are shape resonances that occur due to tunneling through the potential barrier due to the rotational excitation with a quasi-bound state here. And you can think of this quasi-bound state as sort of quantization of the internuclear motion. And that's exactly the theme here, right? If we want to see quantum effects, quantization will be a key. And this is not just something that is a theoretical concept, but it's really measurable. You see it in peaks in the collision cross sections. And the first experiment where this was, I would say, demonstrated in a very, very clear and clean way, it was about 10 years ago from Ed's group, where they measured these shape resonances in Penning ionization reactions. And this is also setting the stage of what I'll discuss today. So let me tell you what is Penning ionization. Penning ionization means that you have a particle A, which is in a highly excited metastable state, and its excitation energy is sufficient to ionize the collision partner B, which can be an atom or a molecule, whatever you wish. And then it produces ions and electrons. And from an experimental point of view, that's a nice process to study because it's a super easy to detect reaction because you have to count ions. And what was key really to the measurement of these resonances as shown here was a technique that was developed that allowed control over the collision energy over many orders of magnitude, which was pioneered by Ed and also is used by Andreas Osterwalder's group at EPFM. Okay, so here are these resonances, and as I said, you can do this with atoms, you can do this also with molecules. Now, if you collide with molecules, the first question that you can ask is, does it matter that you have here some more structure than with just an atomic collision partner? And this is where resonances can become really useful, and I added this slide because one of our chairs is here, co-author, and I see also many people actually in the audience who contributed to this work. And Wojtek also is here, who did the theory on this in my group at the time. So what resonances can be useful for is to probe the anisotropy of the potential. So here is these hydrogen molecules in J equals 0 and J equals 1. And it turns out, because of the connection between spin symmetry and rotational symmetry, that only in the J equals 1 case, there is another shape resonance that is seen here. And at some point, we made the theory match with this very nicely. So we can probe this anisotropic contribution to the potential. Okay, so here's once more the idea that is used in Ed's lab, where they merge these two beams and measure these resonances. And over the years, so the first experiments date back more than 10 years, I said, they of course have evolved significantly and can measure not just the reactive cross-sections from the penning ionization, but also elastic cross-sections. And that held a surprise for us, namely the blue ones here is the penning, the reactive, and the red one is the elastic. And you see that the one peak is almost identical for the two, but the second one is not. And of course, the question is, why is that? And since our theoretical modeling matches the experiment extremely well, as you can see in this comparison between experiment and theory, we can now use the theory to answer this question. Right, so what we have to do is we have to inspect the resonance wave functions that correspond to these two peaks. And it turns out that the low energy resonance, which is this one, is fairly localized behind the rotational barrier. It's the black curve here. And then when you multiply the wave function with the ionization probability, you get this part. So the ionization happens mainly at the repulsive barrier, and that gives rise to these low energy peaks. Now, for the higher energy, okay, the resonance wave function is the one shown in red here. You see it's an above the barrier resonance, quite confusing, a real quantum effect. It's quantum reflection due to the potential. And if you now multiply this elongated, spread out wave function with the ionization probability, which is localized at the repulsive barrier, you get only this much smaller contribution. And that explains why here the peak is small. Okay, so we can, this difference in the cross sections tells us something about the shape of the resonance wave functions. So we can distinguish between quantum tunneling, which is the case in the low energy resonance, and quantum reflection, which is the case in the high energy resonance. Okay, but these differential cross sections can tell us even more, because we have angular resolution, which so far in the argument we haven't really used yet. And this is work I should highlight was the PhD of Prana, who's also here in the audience. So if you have questions about those experiments, please talk to her. So we can use this angular information, and when we now look at the resonance profiles for each of these angular segments that are indicated here, we were in for another surprise. And that was that the profile turns out to be different, and not only different, but in some cases very asymmetric. So asymmetric profiles, for those who are in the scattering or also photoionization business for a long time, they have seen that before, is typically associated with the interference between a quasi-bounded and the background continuum. And this is so-called Fano profile. And then you have this asymmetry parameter Q that determines how asymmetric your profile is. Okay, so in a Feshbach resonance, for example, you have this type of scattering, and then you would expect potentially asymmetric resonances. But we were looking at the shape resonance. So it's a single channel. There's no coupling between the green and the black channel. There is only one channel. So why do we see this asymmetry? And the reason is we look at differential cross-sections. Right? So if you write out the expression for the differential cross-section, you have to sum over all the partial waves which are there. And we can single out the resonance partial wave, and then all the others which define the background. And now, essentially, all that you have to do is to multiply out this square. That gives you the two quadratic terms. One is a Lorentzian for the resonance and some background, which you can roughly treat as constant at low energies. And then there's the interference term between these two. And this is what gives rise to the Fano profile. And the Q parameter is connected to the phase of the background. Okay, and indeed, if you integrate over the angle theta, then this interference vanishes. and you're back to the standard picture of single channel scattering. Okay, now we can test whether this simple picture is really true by comparing our full theory, including all the coupled channels and the full potential, with just a simple model where we have interference between a resonance and the background, which is the gray curves here. And you see, if you compare the gray curves and the blue curves, that the agreement is pretty good. And the reason where we the two versions where we don't see such good agreement, the resonance is not sufficiently isolated. So our assumption breaks down. Okay, and now I come to the main part of the talk, and this is, I want to emphasize resonances allow us to understand the potential really in a multifold way by providing quantum fingerprints of the dynamics. And what we're looking at now are reactive collisions with strong anisotropy. So now we move from the entrance channel of the panning ionization to the exit channel. So what the panning ionization does is it prepares sort of a half collision. But before I get to that, let me connect this to earlier work in the field that maybe some of you know from the group of Koch at Harvard, where they also looked at reactive collisions with very strong anisotropy. And in their case, they found that their final state distribution in this cold reaction, even though it happens at super, super low energies and temperatures, was statistical. Which, in my perspective, being interested in quantum effects is a little bit disappointing. But what do I mean by statistical? So they were colliding KRB molecules, state selectively prepared in the vibrational and rotational ground state, with another KRB molecule, producing K2 and RB2. That's the reaction. And then you can go take the energy that they are providing in the collision and look at the angular momentum conservation and work out what are the final states which are allowed according to energy and symmetry, angular momentum selection rules. And there are 57 final states that can be populated and that are populated. And out of these 57, 50 follow the prediction of a statistical model, meaning the population is given just by counting states and their multiplicity. Okay? So almost all of it, 50 out of 57. Now, in our case, when we analyzed the products of this half collision, so you're preparing a molecular ion which collides with either neon or helium, and then measure the rotational vibrational state distribution, the statistical model failed. Okay, the statistical model here is shown by this dot-dashed curve. You see, for example, this peak, the blue is the experiment, the theory matches the experiment reasonably well, but there's a clear distinction from the statistical model. Even though our energies, our collision energies are higher, and the anisotropy, I think, is comparable to Koch-Green's case. Okay, and this was true both for, no matter whether the experiment was done with helium or with neon. Okay, in both cases, the statistical model clearly gives really wrong predictions. Okay, but the theory works very nicely, so we can ask ourselves, and I would like to highlight, I think Arthur is also here, so another co-author of the work is in the audience. So what happens? Here's our entrance channel, panning ionization, okay, for the case of helium. We ionize at about this position, and then we have a couple of channels which are energetically allowed with different vibrational and excitation. Rotation isn't changed. Okay, so we can have, for example, V equals 2, V equals 1, V equals 0, higher V's. Now, if the wave packet ends up in V equals 2 or V equals 1, then these curves are, of course, only sketches. It's not the full truth because they're actually coupled. There's a lot of non-adiabatic couplings because of the anisotropy of the potential. Okay, so we can convert vibrational energy into rotational energy. So as the wave packet moves down, slides down these potentials. Okay, now we were kind of lucky in a way, because if you look at our initial state for this half collision, is this shown here in red, and you see that in these cases, it overlaps very, very nicely with Feshbach resonances, vibrational Feshbach resonances. So here's the case for V equals 2, here's the one shown for V equals 1. And why were we lucky? Well, there are many such resonances. Each of the peaks which are shown here in this cross-section corresponds to one. But you see, they're fairly isolated. Okay? And it's this isolation that then turns out to result in these fingerprints which are specific to the collision and which are not just an incoherent average over many statistically allowed final states. Okay, so we were lucky that this molecular system has this property of fairly isolated resonances, but we were also lucky of collaborating with the right experimental group. And Ed will speak about what was really behind there, I think, in more detail tomorrow, because they are actually able, by a technique they developed, so the student here was Baruch Margulis, to isolate the contribution of different vibrational states from the experimental data. And then this way we can distinguish, for example, whether we are in V equals 1, we are looking at the Feshbach resonances associated with vibrational excitation 1 or 2. And again, this works both for neon and for helium. Okay, so we have this, I would say, fairly satisfactory agreement between theory and experiment. So now we can ask a few more ambitious questions. For example, how predictive is our theory actually? And for helium, we were lucky once more, because helium and H2 plus is almost the simplest system that you can think of having in an experiment. And the potential there can be calculated at the full CI level. For neon already, it's not that simple. So there are 3 potential energy curves that we have used in our calculations. And you see the theoretical results for the cross-sections are given here by these small peaks. And then we convolute with the experimental resolution and compare to the experiment, which is shown here in gray in all 3 cases. And you see that once we do the convolution, there is a bit of a shift of the peaks with respect to this green potential, which is worse than the other 2. But for example, between the blue and the red, which is a coupled cluster calculation and a multi-reference CI calculation, we cannot really distinguish. The experimental data cannot tell us which one of the potentials is better. But then, of course, we can say, let's assume Ed is able to further improve his experiment. How far would he have to go in order to be able to distinguish these 2? And the answer is actually not that far. Okay, so here's a calculation where we assumed a resolution. So the yellow curve assumes a resolution better a factor of 10. That's quite a lot. But the purple curve is just a resolution better a factor of 4. And now you see clearly that the predictions from the red and the blue and the green potentials are different. And this is true. Here shown are 2 resonances for orthohydrogen and 2 resonances for parahydrogen, this same story. So if they're able to improve the experimental resolution by about the factor of 4, maybe 3 is also sufficient, they can tell us which of those ab initio potentials does the better job. Okay, so here the experiment would be the adjudicator. But of course, we can also ask, given the currently already available experimental data, can we do better? Can we use this to improve the potentials? Okay, and this is of course an idea which has been around for a long time. It's currently seeing a lot of resurrection under the label of machine learning, but I think the idea really goes back much longer, and one of the proponents is also here in the audience. So this is work of Jeremy and Markus Muley at the time in his group, and it's the idea of morphing potentials. What do I mean? It's a transformation of the coordinates, in this case a linear coordinate transformation, could also be nonlinear, and the scaling of the energy. And the idea is, can we find optimal values for these blue parameters by trying to match the experiment and the theory better to the experiment. So R, uppercase R, lowercase r, and theta are the three angles which are relevant for the scattering in our case. So this is the intermolecular distance, R is the vibrational coordinate of H2 plus, and theta the angle. And now you have to think a bit carefully how to do this morphing. So you can expand your potential, and you have then single body terms of the three particles, and then you have two body terms, and you also have a three body term. And usually the argument is, well, the three body term, probably the job of the ab initio calculations is worst in this case. So you can do this transformation either only for the three body term, or you can do it for the whole potential globally. And I'll show you results for both. Okay, so here's the basic idea for those who are interested. Is kind of a feedback loop similar to optimization or also machine learning, where we start with the ab initio calculations, do some kernel fitting, carry out our scattering calculations, do a lot of post-processing, then evaluate how good is the match, and based on this match, either we are done because we're happy with it, or we modify the potential by applying this morphing transformation and start the loop again, going around here until we're stopping. Okay, so here are some results where we only modify the three body term, and for neon H2 plus with ab initio surfaces, all calculated by Markus's group, at the full CI level, MRCI level, and NP2 level. And this is now for helium H2 plus, I should say, because this is a nice benchmark system. So you see, and what is shown here is the change in the cross sections, and then just the difference between the peak positions and the peak heights. So what you have to compare is the difference between the circles and the squares. And you see for the peak positions, they were already captured pretty well in the initial ab initio surfaces, but the peak positions do undergo some changes up to 30%. And then, of course, you should check how does your potential energy surface actually change. In the case of the full CI, not much. Mainly the anisotropy in the long range is modified. And that improves the peak heights, and it's not so surprising because it's the anisotropy which governs the rotational redistribution. So that's in line with our physical intuition. However, if you compare the potentials here, then you see that if you start with a very low quality potential, MP2 level, then the changes that are induced by this procedure are actually unphysical. So you have to be a bit careful with the results. And it tells you that just modifying the three body term is not enough if also the quality of the two body terms is insufficient. Okay. So let's then do the global morphing and allow all of the potentials to be modified. And now I'm just showing you the results for the MRCI and MP2. And you see that in this case, the results, the changes are much more reasonable, and we also get an improvement. And interestingly, the modifications now are again essentially in the long range and near the repulsive wall. And what you cannot really see here, but I'm telling you, there's no correction of the well depth, which for these two ab initio methods is quite wrong. So, but if you think about it, is also not so surprising because the Feshbach resonances, which are probing the potential, are fairly delocalized, and they are mainly sensitive to the long range. Okay. So given the experimental data, we don't have enough information to correct the wrong Valdex. We would need to have to augment this by spectroscopy, for example, or something that probes the potential at the equilibrium distance. Okay, and finally, to confirm this assessment, we have tried to morph the MP2 potential into the full CI potential, not comparing with the experimental data, but comparing with the full CI, just to see if this is possible at all. And if you compare that here, that indeed the potentials are becoming more similar, but global changes cannot be accommodated. So the morphing transformation, as we have shown, keeping the angle the same, doesn't do the job. Okay, so let me summarize this part on the half collisions. The final state distribution is not statistical. Instead, it shows quantum fingerprints, which are typical for the specific reaction system. We have an excellent agreement between theory and experiment, and we've seen in multiple ways it's really the long range that matters. And only slightly better experimental resolution is required to distinguish different level of theory predictions. We also have open questions. Ask me about if you're interested or watch out in the future. And with this, let me summarize the overall talk. So I've showed you how quantum resonances probe the anisotropy of the interaction, allow us to distinguish between tunneling and reflection, lead to asymmetric profiles, and provide quantum fingerprints. Last but not least, this has been a very long-standing collaboration, close collaboration between theory and experiment. Students in my group were Karl Horn, Alexander Blech, and Daniel Reich. Here's Ed's group with the students who were leading those experiments, Yuval, Brenner, and Baruch. And I also want to highlight help from theory colleagues, in particular from Nijmegen, Ad van der Aalvoort and Marcus Mooney in Basel for the more recent work. Thank you for your attention.
Thank you very much, Christiane. There are already questions.
This is your.
So I'm very interested in the morphing part of the talk for obvious reasons. So you commented that you don't have data that tell you the well depth here. Are your calculations accurate enough? Two questions really. Are the calculations accurate enough that they get the number of bound states right, or is that still something that would need to be determined from spectroscopy?
So the nice thing about this benchmark system is that we do have full CI calculations, and the full CI calculations get the dissociation limit correctly. And I believe also the number of bound states, although I would have to check this with Marcus. But
the second thing is, I mean, it's fairly straightforward to put in angle dependence in the morphing parameters.
Exactly.
Is that something you've tried?
We haven't tried yet, but that's the obvious next step. Yes.
Thank you very much for this nice talk, and I should also say that I'm amazed by this kind of a morphing, or we can call fitting the potential. And one comment, this is like a kind of a challenging to have the potential which is correct in the long range and short range part. So are you going, or would you plan to also include the spectroscopic data in your, let's say, morphing or not?
If it's available, of course. That would not even be a technical issue. The problem is that at least for helium H2+, there is no high resolution spectroscopy. Surprisingly, maybe, but there isn't.
While Caden maybe wants to come down already, are there any further pressing questions? Oh no.
So I have a question.
He's taking over the other microphone.
I have two questions. So one, in fact, the theory both for interaction with helium and neon should be able to predict somehow theoretical uncertainties, right? So did you study this? Did Marcus, because like this kind of calculations, you should be able to estimate uncertainties. Of course, there is kind of disagreeability up to some factor, but did you somehow try to see how much this morphing compared to uncertainty of the theoretical potential energy surfaces?
Yes, so I didn't put the table that we have in the manuscript, but I'll be happy to show you in the
okay.
break. Yes, of
Okay.
course.
Yes, and the other question would be, because also for the long range, like for helium especially, the long range in fact is known very, very well, right? So we can have, so then, yeah, this probably in the paper we also compared like somehow this morphing, how far you go from the very exact long range that you can get from monomers properties and long range perturbation theory, right?
Exactly. I mean, the main reason why in the comparison of the three potentials, so let me go back to that slide. Here, the main reason why the comparison for Markov's potential, the coupled cluster calculation, is much better than the two MRCI calculations is that he made sure that the long range is treated correctly, whereas those other works, they were interested in reactive collisions and the reactive pathways, so they didn't care about the long range, and I think that's
but
because for what they wanted, it wasn't that important. But as soon as you take care of the long range, you get the resonance positions.
But did you include, because I mean you can take really like multiple expansion with the properties of neon and hydrogen molecular ion that are known very well, much better than any kind of molecule.
So in this case, the lowest order contribution to the long range was sufficient.
Okay. Yes, I think you can.
Okay, so
I will have also one more question later, but
of course,
especially about this conclusion that the long range is more important. So I think that
for the Feshbach resonances, for which they were essentially probing the long range.
But I mean,
the anisotropy in the long range.
Okay, maybe anisotropy, because like for atomic system, right, this would be not. I mean,
I don't think you can easily draw such a conclusion in general.
No, because in general it's not sensitive to long range. It's really sensitive to the volume. And, I mean, please start. Yes,
then you don't have this big role of the anisotropy, which here is really the key to everything.
Yeah. Yes. But
so let's maybe move this discussion to the break, and let's move on. Let's first thank Christiane again.